All right, I've had a lot of people say they haven't read the Extent Tree V2 design documents, and actually I've come up with some new things that are kind of complicated, and so I'm going to just make a video to kind of explain everything, and hopefully people can just watch it and get the idea. So the first thing is Extent Tree V2. It's kind of a misnomer. There's a lot of changes that I want to make, and I don't want to have an individual incompat bit for every one because I don't want to have to mix and match these things. I want them all to go under one incompat bit. Maybe we can name it something else, but anyway, it's going to be one incompat bit and you get all of these changes. That way we can make a clean break and we don't have to like explode our test matrix by testing, one aspect of this change only with old stuff. So I'm going to kind of go through the list. I'm going to do the simple things first, and then we're going to get to the more complicated stuff. So the first thing is the block group root. So this right now we have block group items in the extent tree. I can't spell, and yeah, you're gonna have to deal with my shitty handwriting. And they are indexed on byte number. The problem with this is in the extent tree, everything is indexed on byte number. So what you end up with is like, on mount, we load all of the block groups. So what ends up being is like you have, like this, this, and like, you have a BG item, and like a BG item here, and like one right here. This sucks. They're on mount. We have to scan the entire extent tree in order to load all the block group items. In the best case scenario, we are allocating a block group for every gigabyte. So with a terabyte, it's 1,000 block groups. 1,000 block groups loaded all across randomly on disk. It ends up sucking. 10 terabytes is 10,000 block group items. So this just kind of sucks. And it's spread all throughout the extent tree. So that makes mount times really slow. We see this in production inside Facebook with some of our larger volumes. Mount times can be, several seconds, even on these fast disks, because it's kind of spread all over the place. It's really annoying. So we're going to have a block group tree, new tree, with only block group items. So still indexed on byte number. It all goes into the block group tree. So we can just read the entire tree, load it all up. 1,000, like the 16K node sizes are defaults. The block group items, what they're a key plus, I want to say 3 U64s off the top of my head. So 5 U64s is 45 bytes plus the type, so 46 bytes per 16K nodes. It's ballpark of 400 items per leaf. So 1,000 things, you're talking about 3-ish leaves, which is 4, 1 root node and 3 leaves. 10,000 is, 30 leaves? Is that right? I don't know. Anyway, much smaller, much less to read in, all compact because we update the block groups on transaction commit, so it's going to be relatively spatially located. That works out pretty nice. Easy, simple, nice win. Okay, the next thing is number 2, per block group, oops, that's not it, block group roots. So currently we have, a global, now we have a global extent tree. We have a global blah, 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 global csum tree. Yeah, and we have a global free space tree if you have free space tree enabled, which you should. It's awesome. We see problems, especially with these two items right here. We don't really see it with this one too much because, generally speaking, the extent tree is the big problem, and that limits the impact on this because we only modify the free space tree when we free things, and so we're limited usually by the extent tree. What happens is, and you've seen patches from me on this before, where I stopped running delayed refs in all of these different places because I could do things like create a bunch of snapshots in parallel and delete and relocate and all of this stuff, which would trigger commits, which would then get hung up on the extent root lock, because we have to lock the extent root in order to modify anything, because that's the only time we do delayed refs, is to modify the extent tree. So we get lock contended on the extent tree root. This is really painful. It means we can't really parallelize delayed refs that well. We basically just have to have one thread that does it all of the time, which is super shitty. You see this to a lesser extent with this checksum tree. If you have a lot of threads writing to files and there's memory pressure, we're having to run finish ordered extent. You kind of see this in finish ordered extent latency because we all get bound up on the checksum tree root, and so this kind of like explodes out the ordered extent completion code because we modify the checksums at that point. So this really hurts. The free space tree again is less of a problem, but that's only because the extent tree is the bottleneck here. If we're contending on the extent tree, whoever gets to actually modify the block is going to be the one that modifies the free space tree, and so by default we won't really get contention on the free space tree because we already paid for the contention on the extent tree. So, but in order to address this problem, we want to split all of these trees up. So this gives us kind of two nice things. So like, we have an extent tree in the worst case for the normal case, not worst case, for every 1 gig. Same for the checksum tree only for data block groups, and every data block group. And then, again, same for the free space tree, every block group. So this splays out everything, splays out our locking. Clearly, if we're modifying the same block group a lot, this is not going to help too much. But in general, if you have a relatively large file system with a lot of processes hammering on the file system, you're going to get spread out across the file system in general. So this will help. It's not a perfect solution, but it's like one step in the direction of reducing our lock contention problem. Okay, next one. Relocation. Okay, relocation is complicated. It's super complicated, and it's super error prone. Not error prone, I should say. It's very fragile. So currently what we do, for those who are not familiar, so we have like fs tree. What we do is for relocation, we create a relock tree, which is just a snapshot. It's like a special snapshot of the fs tree. And then we walk down And so if we're going to relocate block group, 1 gig. So like we want to relocate everybody in the block group that refers from 1 to 2 gig. We walk through the extent tree and we find any byte numbers referenced in this area, and we copy them somewhere else and we update it. And the way we do that is so if this is a data tree, for example, we walk down the reloc tree, and so say just for simplicity's sake, this file extent bytes number 1 gig. All right, we want to relocate this guy. We copy him out to a new spot. So we say, okay, this now goes to 4 gig, starts at 4 gig. And then what we do is we go through and we find the file extent, and then we update the file extent in the reloc root to point to 4 gig. All right, simple, right? We're not touching FS tree at this point. Now, that's the easy part. Once this stage is finished, we have to go back and we have to update everybody to point at the new blocks. This is where it gets complicated. Because we want to maintain snapshots awareness, if FS tree has 10 snapshots, okay, so this is A prime, this is A prime prime, and these guys all point to this block which has the file extent that we modified. We have to go and we have to, when we cow down to modify this, we have a new block, right? I wish I had let's use a different color. So we have this block, right? So this is block C, and this is C prime. Now we have to update everybody to point at this block, and this is where relocation gets really complicated. And Zygo noticed this, and this is a huge problem because we have to do this all at once. So we look up this new block, or we look up the old block, and we update everybody to point at the new block. So I'm showing it really simply here, where it's like a root pointed at a simple block. But if it's a node and it's intermediate node, we have to cow down to that node on everything. So this is the other thing is we maintain snapshot sharing, sort of. We only maintain it for the shared block. Everything down to that shared block gets copy on writed. So if we shared a node up here, that sharing would be broken. The only thing that would still be shared would be C#. And so then this explodes the number of delayed refs that happens. And so we have to update all of this, and then we can block that guy out, and then this guy points to the 4 gig, and once we delete that, the 1 gig goes away. And that's how relocation works. This operation right here, like I said, it has to be done in a single transaction handle. And this is the problem that Zygo discovered, is that because of this, we suddenly go from 0 to 1,000 delayed refs, because remember, we're cowing down to this block right here. So the entire paths are being cowed for every snapshot that we have. And in Zygo's worst case, he's generating snapshots constantly and running relocation and running snapshot deletion, which just explodes the number of delayed refs that happen to the point where we choke the system out. And that sucks. So what's the solution? So solution: no more reloc root. We stop doing this bullshit here. Instead, we have a remap tree. what the remap tree does, so let's do another, okay, so remap tree. Remap tree says okay, block group 1 gig has X, all right, we're gonna, sorry. The remap tree is going to remap chunks of the block group. So instead of doing what, currently what we do is we walk the extent tree to figure out what blocks are pointed to inside of that block group. Or so like what block groups exist inside that block group. So we can do the snapshotting and all of that stuff. What I want to do instead is to raw copy that data to other block groups and then remap them in their new logical space, and then insert an item in order to remap that block. Okay, that was complicated. So what I'm going to do instead is say find all extents in a block group. So in this case, we say, okay, we're again block group 1 gig, and we find a extent from 1 gig to, I don't know, well, let's just do it like this. Like, say we find offset 1 gig and like size is 1 meg. What we do is we go and we allocate a new 1 meg extent in a different block group. We've already, this is read only. So we allocate a new block and we get, we get offset. So the new is offset, I don't know, 4 gig. And again, size stays the same. Size equals 1 meg. We raw copy to new location, and then we insert a remap item into remap tree pointing at new offset. So now we have in the remap tree remap item, and we have key dot object ID equals 1 gig, because that's the original offset, and the offset equals, I don't know, we'll say offset is 4 gig. We'll say the new offset is this. And then in the item, we'll have like length equals 1 meg. Yeah, that's it. So and then how this works, and that's all we do. That's the only thing we do. And so how this works is when the block group for 1 gig is loaded, we have a flag, set remap flag. When it's remapped, and that'll be, the flag is set after everything is remapped. That way we don't have to mess with it until we know we're finished. So once the flag is set, we know we have a remap thing, and we load it into a extent mapping, blah blah blah, extent mapping. So then when we do a read for 1 gig, we don't change anything else. We don't remap, we don't mess with the metadata, nothing. Everything still refers to the original offset. So then we go to do a read from this at 1 gig, and we see that we're set here, that we're remapped. We look up the extent mapping and say, oh, okay, 1 gig is at 4 gig. and we go and read from 4 gig, which then read from logical 4 gig, which then does the proper chunk mapping or whatever. The Btrfs mapped block bullshit. So there will be an intermediate step that says, okay, am I remapped? Yes. All right, find the new logical offset, do that logical, use the new logical offset, and then remap. The benefits of this is it is so much simpler because we no longer have to maintain this relock snapshot. We don't have to create it if we're doing relocation. We don't have all of the extent references left over from cases where we couldn't cleanly recopy. The other thing is we're now completely data agnostic. Like we have, data agnostic. We don't have to know anything about the data. We just know that we have a chunk of data in this block group that's being used, and we can read it into page cache and write it back out. If it's encrypted, we don't care. We don't have to decrypt it to know anything about it. If it's compressed, we don't care. We don't have to decompress it. We just raw read in the blocks into pages and write them out in a new location. And we don't modify any metadata and we don't break any snapshotting thing. So the original relocation, you would still break snapshot sharing down to the shared node, which could be a leaf. So you would break all of the node sharing. In this case, we don't do that. This makes it so much cleaner and much more simpler to do relocation. And the other nice thing is currently we are limited to 128 meg maximum extent size because mostly because of relocation. Because with relocation, the way the data relocation works is you have to allocate 128 meg extent because we cannot modify the file extents in the FS tree. We can't say break that up into 64 meg because then we would have to modify all of the snapshots to change the file extent, and we can't do that. So you literally have to allocate a new 128 meg extent, and if you can't, you fail the relocation. So if you're fragmented, you can't actually move everything around. Because the remapping is agnostic, it doesn't care, we can split into as small chunks as we wanted. And then we can increase our maximum. We can't because maximum extent size also has implications for ordered extents. But we can potentially break any extent up. In fact, we could even break up compressed extents. So if we say we want, say we broke this up into, 4K chunks, and we do a read for 1 megabyte, we just, create a bio for every, 4K that's remapped here, and then tell this that it's up to date after all the 4K reads have been done. And yeah, it's slower, it sucks, but we have the flexibility to deal with heavily fragmented block groups. And again, relocation becomes simpler. It no longer becomes this thing where only I understand it and only halfway understand it. It gives a lot more flexibility, and there's no delayed refs updates is the other thing. Is like we literally don't update reference counts for anything. We simply remap the logical extents. And then, so what happens, whoa, that's my Spanish homework. Did I close that? Shit. Oh no, come on. Yeah, okay. All right. So the other thing is for freeing. How does that work? It's relatively straightforward. Why does that thing say it's 9:41 a.m.? Okay, whatever. Anyway, when we're freeing remap objects, it works in a similar way, right? So we go to free the 1 gig offset, the 1 gig extent. We do that, or the offset, the 1 gig and 1 meg sized extent. We free that guy. At that point, we remove the remap item for it because we no longer need it. We're no longer referencing it Because of our normal referencing count, we know we're no longer referencing that particular offset. We remove that remap item. So when the remap tree for a block group is empty, we free the block group item. And that's when the cleanup happens. Is after we've cowed everything and we've redone everything, it's fine. It's done. This sort of sucks in that one of the drawbacks is that if you relocate everybody, you basically have to do this mapping. You have to remap everybody on the fly. And so it's like another translation layer, right? You have to look up the extent map to find the new logical address and go from there. This is less painful because that's an in-memory operation, and it's going to be relatively straightforward. Because again, like I said, over here, we can do things in arbitrary sized extents. The same goes for metadata. So if we have block, 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 block here of metadata, with normal relocation, we'd have to relocate each individual thing. Whereas the new one, we can just remap, copy the whole thing wholesale into a new chunk and just say, okay, new offsets. It's like old and new, and all of these guys are represented by one remap thing, and we can more efficiently copy and move things. So it does have a downside, but the upside is better simplicity, more flexibility, no modifying anything, any metadata, and we can maintain better snapshot sharing in the face of relocation. Okay. The next big thing is the extent snapshot tracking. This is not in the original design documents and is sort of complicated. So actually, I think I'll save this for another video.